Hello everyone. Today I'm going to talk to you about Grignard synthesis. The Grignard reaction is an old reaction discovered around the turn of the 20th century by Professor Grignard. It was a big discovery at the time because it was a way of converting an alkyl halide or an aryl halide into a magnesium ion, which could then be used to transform an aldehyde or a ketone to an alcohol. So the main application of the Grignard reaction is to make alcohols. Although the Grignard reagent itself is a very strong base and it could be used as a base, but its application for the most part is to make it in order to make alcohols, whether they're secondary or tertiary alcohols. The experiment that you will be doing is the reaction of 1-chlorobutane and magnesium metal in the presence of the solvent diethyl ether. When you carry this out, you generate the Grignard reagent. So the Grignard reagent, as you can see, is an ionic species, okay? And the magnesium metal has lost 2 electrons. So the magnesium 2+ is kind of sandwiched between the 2 negatively charged ions, okay? So when we form this species, then we can react it with a ketone. And the ketone that you're going to be using is acetone. So another way of saying it, we can trap the Grignard reagent with acetone, and then you get what is called a nucleophilic addition to the carbonyl of the ketone, and what you end up with is this alkoxide ion, okay, which has got the magnesium ion in it as well. So this is the first week that you perform this reaction. This synthesis actually involves a 2-week lab period, but because the reaction takes a very long time, we've broken it out into 2 weeks. And one of the reasons that it takes a long time is because it's not very easy to make the Grignard of chloroalkanes. Generally speaking, making the Grignard reagents from an alkyl bromide or an aryl bromide, it's much easier because the carbon to bromine bond is much more easily broken than a carbon to chlorine bond. So this reaction takes some time. As you can see later on, when I'm going to demonstrate how this reaction is done, you can see that it takes quite a long time for the Grignard reagent to form. So as soon as this first reaction is complete, you add the acetone, and of course the solvent continues to be ether. And then once you reach this ionic form, traditionally we would stop the reaction during the first week and come back the following week to carry out the protonation reaction. So we're going to have to protonate this alkoxide ion to the alcohol. And of course, the inorganic byproduct would be the bromomagnesium hydroxide, which just gets washed away in water. Okay? So this is basically the product that you're going to be making in this lab. And as you can see, we have a tertiary alcohol. So essentially, if your carbonyl compound happens to be a ketone, we will end up with a tertiary alcohol, right? If your carbonyl compound was an aldehyde, then we would end up with a secondary alcohol. So this is the entire synthesis, okay? The one thing to remember is that when you actually set up this reaction, all the glassware that are used to make the Grignard reagent has to be scrupulously dry. Any trace of moisture is going to hinder formation of the Grignard, okay? So your ether has to be anhydrous, that means it's completely dry. The magnesium turnings has to be dry. The starting material has to be dry. And of course, the glassware has to be dry. So this is a reaction that really requires a very dry condition for the reaction to be successful, okay? And the trapping of the Grignard using acetone is actually quite an exothermic reaction, okay? In fact, when you see the reaction going, you'll see how fast this trapping of this Grignard is going to be with acetone. In fact, it's so exothermic that you have to cool the reaction mixture at this point, okay, in an ice bath for like 5 or 10 minutes before adding the acetone dissolved in ether, okay, and only dropwise. So you can't just pour the whole acetone into the flask and then expect that the reaction is going to behave fine. No, this thing is so fast that it could get really out of hand if you don't add the acetone ether solution dropwise very slowly. And you can see how fast that reaction is in a few minutes when we do it. Once you finish adding the acetone, then the reaction actually is pretty safe to stop. Okay, in other words, it's pretty safe that you will remove all the other equipment. The reaction is no longer sensitive to moisture, and it's pretty much easy to carry to the next step. Now the next step that I put H3O plus, actually the way you break this cake, the way I call it, is by putting in 2 different types of acid, right? The first one is a weaker acid. You will put in ammonium chloride so that you start the hydrolysis in a pretty moderate way, right? In a controlled way. And then you add hydrochloric acid. So there are 2 acids used. First, ammonium chloride, so that the reaction starts hydrolyzing slowly, because you don't want it to go berserk. And then you add the HCl, and then you realize that this insoluble magnesium salt actually becomes soluble. And you end up with 2 layers, one layer which is the ether layer, and the other is the acidic aqueous layer. And then you're pretty much ready to separate your layers, wash your organic layer with some base to neutralize any excess acid, and then of course recover the organic layer, which is the ether layer containing your tertiary alcohol. And then what you will do at the very end is remove the solvent, remove ether safely. Remember, ether is extremely flammable. You don't want to, use excessive heat. Ether boils at around 37, 38 degrees Celsius. So you need, you could just use a water bath to remove ether, which is something else that I'm going to be demonstrating. And then, of course, once the ether is safely removed, then you can distill your tertiary alcohol at a higher temperature. You look up the boiling point, and you could just do a simple distillation, and that will be basically the end of your synthesis. But then notice you have to weigh your product and calculate the percentage yield. Okay, so technically you would have to find the number of moles of the chlorobutane and then the number of moles of magnesium to see which one is the limiting reagent, and then based on what the limiting reagent is, you can calculate the percentage yield of your product. Okay, so there's a lot more that you can read about the Grignard synthesis. But I think I'm going to stop at this point, and because it's a long reaction, and you will have a lot of questions for your instructors. Okay? So have fun.
Hello everyone. So we are going to follow the procedure, and the procedure calls for 2.4 grams of magnesium turnings. Here we have magnesium turnings. And so I'm going to measure 2.4 grams. First I need to tear away the paper. That means zeroing it out so that I know exactly that I can start from 0. So I need 2.4 grams. Okay, added a little bit more. So we have exactly 2.4 grams or thereabouts. This is going to be in excess, so you're not going. It's going to be quite a bit left over after the reaction. So I'm going to add this to the round bottom flask. So because I already have this set up ready, it's going to remove this. Add the magnesium turnings. To the neck of the round bottom flask. Make sure there's nothing getting stuck at the neck. And then it says, to this add 15 milliliters of anhydrous ether. So I have the anhydrous ether here, which has been sitting in the refrigerator. I'll open it up. And I need 15 milliliters. So this thing I think was wet, so we can't use anything that's wet. Let me remember, one thing about the Grignard reaction is all your glassware has to be scrupulously dry Otherwise the reaction won't start. So this is a 10 ml graduated cylinder, so I just use this twice. Again, this is a solvent. You could have a little bit more or less. It's not that crucial. So there is roughly my 15 milliliters of ether. And then I put the setup back on the round bottom flask. So as you can see, the setup involves a round bottom flask, a Claisen adapter, a column or a condenser, and an addition funnel or a separatory funnel. Okay? So the idea is that we're going to add the reagent, the 1-chlorobutane, in this funnel, so that we can slowly add this to the magnesium turnings so that we get the Grignard reaction started. And hopefully it's a dry day and the reaction can start. Next step says add to the separatory funnel 10.5 milliliters of 1-chlorobutane. We don't have anything that can measure exactly 10.5 milliliters, it would be approximate. So the best thing to do is actually weigh this liquid. We have its density, so we can weigh 9.3 grams. So the procedure calls for the 1-chlorobutane, which is starting material, to be 9.3 grams. So I could just add this slowly to this beaker until I get close to 9 grams. I went a little overboard, so I could just take out remove some reagent to get it to 9.3 grams. I don't put it back into the bottle, I just need to discard this. Okay, so I have exactly 9.3 grams, which I'm going to add. I'm going to add that to the funnel. And then it says to add ether to this. It says add 30 ml of anhydrous ether. So this one we can measure using a graduated cylinder. Again, it's okay to get a little more or less because this is simply a solvent. What needs to be accurate is the amount of the reagent, which is going to be, in coordination with the magnesium, right? So we'll add this. This is nicely mixed. So as you can see, I have in this round bottom flask right now sitting the magnesium turnings together with the ether as a solvent. And to this, I'm going to be adding 1-chlorobutane, right, which is also dissolved in ether. So we can actually start spinning this. And then I can slowly add the reagent. Okay, so a couple of things to be mentioned here. First of all, the procedure calls for a drying tube, right? Today is a very dry day, so we don't need to really use a drying tube. The reaction should work in the absence of having drying tube on the top. One thing which is crucial to have is you need the water in the condenser so that the condenser is cool or cold enough that when the reaction starts and the ether begins to boil, then it will begin to reflux, so you won't lose the solvent. So we're adding this. It says add about 1/3 of this and swirl the flask for 2 minutes. So we can just add it a little faster, because again, as I said, this reaction is very slow. And then I'm going to stop and really increase the spinning a little harder to make sure this thing is being well stirred. And what you really need to have is you need to expose the surface of the magnesium to the reagent so that you get the initial reaction going. Now again, this will take some time, but sometimes while you're waiting, if this reaction doesn't start, the procedure calls out for starting the reaction in a test tube. So I have a test tube here. You really don't need to measure anything accurately here. So I could just add some magnesium turning to this. I'm really just eye measuring. It's not crucial to weigh anything because I just want to initiate the reaction in case if my setup here doesn't get started, I can basically get the reaction started in here and feed it into the main reaction to basically initiate it. Okay, so I'm going to add some ether to this. Again, no reason to measure. And by the way, we're not really heating anything right now. Otherwise, I wouldn't be opening the ether next to a hot plate. This is simply stirring. There's no heating. But it's still always a good practice to keep the ether bottle away from any source of heat. So here is the N-butyl chloride. Again, I'm not going to be measuring, just going to be adding. Okay. Okay, so as I said, I have some magnesium turnings in this test tube. I added some ether and the 1-chlorobutane. Again, I didn't really measure this. I measured it. The reaction should start, and so what I'll start doing, I start stirring this, not too hard, otherwise I will poke a hole through this test tube. So the idea is to get the oxide layers off of magnesium metal so that the surface of the magnesium has a chance to come in contact with 1-chlorobutane so that the Grignard reaction can begin. So this you have to be a little patient. because, again, as I said before, the Grignard reaction involving 1-chlorobutane is a very slow reaction. So just take your time, be patient, but the reaction will start, I promise you. In the meantime, this thing is also stirring. So my guess is the reaction is going to start either in the test tube or in the flask, whichever one first, that's good enough, okay? So we can continue to hook onto this magnesium. And one of the signs of the reaction when the reaction starts, the solution begins to get a little turbid, like a slightly milky color. And you know that's the positive sign that the reaction is going to begin. Okay, you can see after stirring this for a few minutes, the color of the solution becomes turbid, and soon this Grignard is going to start, and you can see the solution. In fact, it started. Look at it. It's beginning to boil, right? So what you're seeing, I haven't introduced any heat in this reaction, but the reaction is spontaneous, and it's the ether that is basically boiling and getting the Grignard going. So my reaction started faster in the test tube than in this flask, and that's what I predicted. But that's okay, because what I could do, I could just take a little bit of this active Grignard solution and feed it into my reaction mixture, and I would expect that the reaction will start as well. So let me try that. Yeah, this thing is really going pretty vigorously, as you can see. So this is quite alive. So with a disposable pipette, you can just pick this up for a minute and hold it on the bottom. Yep. So I'm going to add this highly active Grignard into this flask. Okay, so this thing is behaving quite nicely, and you can see now this thing is beginning to get turbid, and most likely that reaction will start pretty quickly. So I'm just going to leave this here. Increase on the spinning a little bit to make sure that the reaction is not going to die. So this will take some time. So you can see that the reaction is starting on its own. It took a little time, maybe about 10-15 minutes, but now it's going spontaneously, okay? So while it's doing this, I can slowly add the rest of the reagent. Adding the rest of the reagent dropwise. Also, I need to get a nice way of having a reflux with type of the same rate of the addition. This way the ether won't really escape out, right? So maybe I'm adding a little bit too fast, so I can slow this down a little. And you can see the reaction is boiling on its own because the Grignard has started, and it's also refluxing. You can see the ether refluxing from the condenser back into the flask, and the reaction is going. So this is this is a successful Grignard reaction, right? As I said, it's hard to get it started, but once it starts, you can let it go, and it's gonna take about another 30 minutes after the addition of 1-chlorobutane and ether for this reaction to subside boiling, and then we can heat it for a 10-minute extra to make sure the reaction has completed before quenching the reaction with acetone, the second reagent that I talked about, right? So we have a nice rate going. We're adding the reagent, and the reflux is going quite nicely. So as you can see, all the Grignard has reacted. There's no more bubbling. The Grignard reagent is formed, and we're ready to take this to the next step, which is by quenching it with acetone to make the alkoxide ion. Okay? So the procedure calls for 7.6 milliliters, but I can't measure exactly 7.6 milliliters, you know, using this. It would be very approximate, right? So I can weigh it. It would be exactly 6 grams of acetone. So I put this on top of this balance, zero it, and I'll add 6 grams of acetone using a disposable pipette. And I can control that because I can add it dropwise. It's not such a great ball. So I have right now close to 3 grams. .2. So remember, I want exactly 6 grams, right? So now I have to add slowly. Until it reaches exactly 6 grams. A couple more drops. I have exactly 6 grams, 6.03. That's pretty good. So I will add this. So I will add the 6 grams into the set funnel, 6 grams of acetone. And to this, I'm supposed to add 15 milliliters of ether. So that I could just quickly measure inside this graduated cylinder. That's a 10 ml. Again, the amount of ether doesn't have to be exact. That's only a solvent. So that was 10 ml. I'll add an additional 5 milliliters. Okay. Now, everything is ready to go, but I have to do something very, very crucial, and that is, I'm done with this hot plate that was used only for stirring purposes, not heating. And I'm going to cool this to zero, down to zero, because the addition of acetone to the Grignard reagent is such an exothermic reaction that I have to make sure that this flask remains extremely cold. Otherwise, this thing is going to go crazy. Okay, so let me just add the ice bucket. By the way, I'm only using one clamp here, right, to hold this thing. It's fine, but if you, just to be on the safe side, you may also want to clamp the condenser. That will make it secure, but you really don't need it because this thing is not too heavy. So I'm going to keep adding the ice. Very important to really ice this up. More the better. Now, ice alone is not going to be sufficient. You have to make an ice bath, right? So I'll add some water to it. So you have to make the ice bath, not just ice, but ice bath. That's how you keep the temperature low. So I got to wait until this flask is completely cold before adding my acetone ether solution into the Grignard. As I said, this is a very exothermic reaction and generates a lot of heat, and we have to make sure the system is really, really cold. So this thing is all immersed in an ice bath, and it's been a few minutes, and this water, make sure this water is running. I'm going to go a little faster than this. Okay. So what I will do, I will add the acetone ether solution to this slowly, and if you really listen, you can hear the sound as it's being added. That's how exothermic this is. I don't think it's recording the sound, but there's a lot of fun going on inside that flask right now, okay? The idea is not to add this very quickly, just very drop-wise, and we can actually shake it. I can loosen this a little bit, so I shake this. And I can see if the reaction goes really too fast, ether really begins to come out, and you don't want that. That's why you need the cooling condenser to be really efficient. You have to make sure this is cold enough so that the ether doesn't escape out. See the ether coming out. You can actually see the same rate of addition becomes the same rate of reflux, right? So that in of itself is telling you how exothermic this reaction is. Even in an ice bath, the quenching is extremely exothermic. Of course, it doesn't take much to boil ether. Still, it's a pretty fast reaction. almost there. I can shake this a little bit. This is probably the hardest step in this reaction, to make sure that you know, that the addition remains at a good rate, and you really won't have an accident, because if you add this too quickly, ether will come out way too quickly, and you will actually begin to smell it, which is not good. But this is doing fine. That's how exothermic this is. Okay, all the acetone ether solution has been added. I really don't want to take this out of the ice bath yet, because still this thing is reacting quite a bit, okay? So I let this sit in there for a few minutes until the reaction, really the quenching, is complete. Okay, so as you can see, we have the Grignard product, that is the magnesium alkoxide, after the addition of the acetone. And now what we need to do is basically acidify it so that the alkoxide turns into an alcohol, right? So I'm going to carefully remove all these attachments, because now it's safe to disconnect everything. So you can see this is our Grignard product, which is like a milky mixture, and that's what we're going to finally acidify, right? So over here I have some crushed ice, and let me reclamp this. So what I'm going to do, I'm going to add some ammonium chloride. Procedure says add 20 milliliters. And you add ammonium chloride before you add hydrochloric acid, because ammonium chloride is a weaker acid, so you don't want the neutralization to take place with a lot of generation of heat. So we're going to acidify it slowly, and so add the ammonium chloride to the ice, and then we can add the Grignard product to that. Just swirl the mixture and keep pouring it in. You can see it's pretty safe. Yeah, we could actually add in a little bit ammonium chloride to the flask to wash this off. And it seems like there is very little bit of magnesium is left that has remained unreacted. So that's a good sign that the reaction has really gone to completion. Okay, so this is good. Now I can stir this up. Now you begin to see two layers, right? The ether layer and the Grignard product, which is now being acidified to turn into an alcohol. You can see slowly that cake-like material is going into solution because it's getting protonated, and it's looking good, right? The next step is to acidify this with hydrochloric acid to the pH of 4 to 5, okay? So here I have some hydrochloric acid, and you know, I'll take my pH paper out. And cut a few pieces to test for acidity. Aha! I just added a little bit, and you can see it started to neutralize quite a bit. So I can just check the pH. It's still, yeah, it's showing neutral, but pH of 4 or 5 should be kind of orangish yellow on this pH paper. So I can add a little more acid, and it's okay to have add excess acid. It doesn't really harm anything. And this is you know, 20% HCl. It's not really that strong of an acid to cause dehydration of the alcohol in an ice bath, so that we don't need to worry about. Okay, now it's acidic, and now we can transfer our solution into a separatory funnel. Now you can see tiny amounts of magnesium that was left unreacted from the reaction is reacting with the HCl and producing some hydrogen gas, right? So so now, of course, since we have to shake this up, we have to be careful, because this thing, you know, once we close it, it's going to build up a lot of pressure, right? So in the meantime, I could just stir this up to help hydrolyze to complete the reaction of excess magnesium with hydrochloric acid. The alcohol is already formed, so you can see the two layers, right? We have the aqueous layer in the bottom, and we have the ether layer on the top. Ether is lighter than water, so it stays on the top, and of course the alcohol that we now produce is going to be in the ether layer. Okay? So I'm going to be brave and try to shake this, but with venting. Okay? Venting is very crucial when you're generating gas and you want to close this. You've got to make sure you vent enough, right? So if I do, I'll close this. Remember, I'm building pressure already. I tilt it and I open, right? Shake, open, shake, open, and I can give it a nice shake. Not a lot of gas is being produced, which is a good thing. And the last final shake. So this is really an extraction, right? So we allow the layers now to separate. And I can still see some bubbles of hydrogen still being produced, but it's no big deal. So once the layers separate, I can get ready to get rid of the aqueous layer. Let's see what the procedure says, right? Okay, you can see now the layers have separated. Again, there's tiny bits of magnesium still reacting at the surface. I wouldn't worry about that. So I can now separate the layer. I don't really need the bottom layer anymore, because that contains the aqueous layer and all the inorganic byproducts. So as soon as it gets closer to the top layer, I'm going to close this. Okay, and by the way, this I don't need anymore, right? This is the aqueous layer. I'm finished with that. So I can actually wash this down the sink. Okay? To the organic layer, I want to add sodium carbonate to neutralize any excess acid. So I add 20 ml of 10% sodium carbonate. And that takes care of any excess acid that might have been there. So I'll give it another shake again with proper venting. See, this one produced a lot more gas because I was neutralizing the acid base, right? Still quite a bit. So this venting is really crucial. You can't just keep shaking without venting, then you'll have a little explosion in your hand. Okay, now that it's safe, all the gas is gone, you can give it a nice shake. And then allow the layers to separate. Again, what we're interested in is the top layer, right? The bottom layer is still the aqueous sodium carbonate extract. And this mixture must already be neutral, right? Of course, you can check that with a pH paper. Okay, so let me withdraw. One common mistake is people forget, you know, when you put this on, some people forget to remove this before withdrawing the solvent. And look what happens if you forget, you know, and then you add this thing is going to stop coming out because you need the air pressure to push this out, right? So always remember to open this before doing your separation. Okay, so I'm done with my aqueous extract. This one has some inorganic byproduct. We don't have to throw this down the sink. We don't know what it is, so we'll just pour it into the waste. Now I'm going to allow the organic layer to drain, and I'm going to dry the organic layer. I've got sodium sulfate, same thing. It's anhydrous sodium sulfate, right? And your procedure says to weigh this, but you could eye measure this. It's not crucial. For this much liquid, you just see how much I'm putting in, right? Maybe you should measure. I don't need to measure. It's like a teaspoon full of sodium sulfate. Now the purpose of adding sodium sulfate is to dry the organic layer, right? Dry it from what? Drying it from water, because remember, when we do extraction, there is always tiny amounts of water which will always remain in the organic layer. And of course, ether is not soluble with water, but still some droplets of water still remains in the ether layer. And of course, since we've just made an alcohol, you may have some water that may be stuck to the alcohol. So by putting in this drying reagent, we are basically removing any undesired or excess water from this mixture. So now you can just leave this there for 5 to 10 minutes, and then when that is dry, we go to the next step. Okay, so after 10 minutes of drying, the ether solution containing the alcohol is ready to be gravity filtered to remove the drying reagent. So we're done with the drying reagent. You can see how nicely the solution is nice and clear. So technically, what we have in here is our product and the solvent. So we want to remove the solvent, right? It could very well be that there may be some unreacted butyl chloride, but that you could get rid of through your final simple distillation. But right now, I just want to show you how we will remove the ether. The procedure described in the book talks about ether removal using a simple distillation. I want to avoid that because I don't want to produce heat directly next to ether, so I'm going to use a different technique of removing the solvent here, which is much safer, and that is through vacuum distillation. We get ready to remove the solvent. So what will remain behind after removal of the solvent is your product in this large flask. And then you transfer that into a much smaller flask to do your final simple distillation to recover your tertiary alcohol. Okay, so we're done with that. Now I'm going to show you how we're going to remove this ether using vacuum distillation. Okay, so here is the setup for a vacuum distillation. And as you can see, we have a setup here by which we are creating vacuum through a pump. Maybe we can show that. And we generate the vacuum through this line, and then we will make sure that this thing is going to be pulling the air, and at that point we will put the flask. In the meantime, I'm going to just demonstrate. So I open this to air. You can see how this is pulling. So I will put this on. I will close it. And I will rotate it. You can see the solvent, the vacuum is so strong that the ether is already boiling as I'm placing it here, right? So this is the same as a simple distillation, except I'm applying vacuum to the system, and of course ether being as low boiling as it is, it's not even going to need much heat for it to evaporate, right? So over here I have placed quite a bit of ice in the condenser, and I also have a trap down here. Then I can slowly push this down into this water bath, and I can add more ice here. Make sure the ether doesn't escape, even though some of it will always escape. Okay, so you can see, if I bring this up, you can see how this is nicely boiling, right? See how this is boiling. And I'm not even applying any heat into this water bath. So the vacuum is strong enough to bring the ether to a boil. Remember, reducing the pressure, which is what we're doing here, will reduce the boiling point of the solvent. Okay, as you can see, the ether is now all evaporated. I'm going to start spinning this thing and allow air to get in. This thing is already holding, and take out the flask. So this is basically your product, because all the ether was removed. So now I will transfer this into a small flask to do the last step of the final distillation. So I have the simple distillation set up. I'll just remove the thermometer adapter and add the compound through a funnel. Back. Of course, I got to add a few boiling chips. To the flask. And I can either place an oil bath here or remove this and replace it with a heating mantle and allow the distillation to go. Don't forget to adding the water in from the bottom, out from the top, right? And then of course you follow the procedure and you boil the solution, which is really your product. It says continue distilling and collect the product between 141 142 degrees. And of course, what I would suggest is before you continue the last step, you should pre-weigh this round bottom flask. This way, when you get the final product in, you have the weight of the flask, then you will have the weight of the product with the flask, and by difference you find out how much alcohol you distilled over. And then of course you can calculate the percentage yield. Okay? So this was a pretty long lab, and I hope you remember all the steps that I described in this very interesting Grignard reaction. Be well.